In this module, we will discuss superconductivity in mesoscopic devices and structures. In this lecture, we will overview the phenomenon of superconductivity, and we will also brush up various important parameters. We will discuss anterior reflections and also review the fabrication of mesoscopic superconducting junctions, tunnel junctions in the laboratory. Superconductivity is the phenomenon of dropping the resistance from finite value to zero at finite temperature for certain materials, certain solids. It was discovered in 1911 by Camberling-Ons, where he observed the resistance of the mercury dropped from few milliohms to almost zero, like few microohms, which is probably the measuring limit of that measuring equipment, in an interval of like 10 millikelvin. Resistance of normal metal also drops to zero. For pure metals, we call perfect conductor, the electron motion is impeded mainly by the lattice vibrations. Because a pure metal, there are no defects or dislocations. So lattice vibration is the main mechanism of, or main contribution to the resistance. And the resistivity should go to zero as temperature goes to zero, because at zero temperature, all the lattice vibrations are frozen. So the curve is going to look something like this here. Okay, as a function of temperature, the resistance will go to zero as the temperature goes to zero. But for impure metal, the resistance also will follow a similar path, but it doesn't go to zero because the impurity scattering is not a function of temperature very much. So that is going to prevail even at 0 Kelvin or absolute zero. For a superconductor, the resistance sharply drops to zero at finite value of temperature. That's what is going to happen in superconductor. Now, this drop of resistance to zero from a finite value for a superconductor can also be slightly broader. That again depends on the width of the width of the transition depends on the purity of the metal, its metallurgical history, and various other parameters. But this drop happens at finite temperature. That is the main signature. Here is a periodic table which shows that many of the pure elements are superconducting at ambient pressure, and few others are also can be made superconducting by the application of pressure. So, just to review the theory of superconductivity, it was the theory was proposed by Burdeen, Cooper, and Schrieffer, and the main point here is there is an attractive interaction between the conduction electrons, which is mediated by the lattice or mediated by the photon. So, an electron which is moving through the lattice can deform the lattice, and another electron which is coming by can feel that deformation, which in nutshell is going to lower the total overall energy of the two electron system. So in more physics terms, the first electron can excite a phonon. That is a deformation that we are talking about, deformation to the lattice, because lattice deformations or lattice vibrations are actually phonons. And the next electron can absorb that phonon. So there is a virtual exchange of phonon, which can be attractive when the energy difference of the electron states involved is less than the phonon energy. So it is an attractive interaction which is mediated by the lattice, mediated by the phonon, which dominates over the screen Coulomb repulsion of these individual electrons. These two electrons can combine and form a bound state. So the ground state of a superconductor is formed by a combination of these normal electronic states. Okay, but if you look carefully, these electrons, the way they combine is they combine or they pair up with the opposite spin and opposite momentum. And this state, combined state, will have a much lower energy compared to the total energy of the individual state. And of course, when you combine two spin states, it doesn't matter what is which way, you always will get a boson, because you have two half integer spin, and when you combine, you always will get an integer spin. So the combined state will always be a boson. And all these bosons, which would like to condense onto one state, that is the ground state. Okay. And now, if you look, where are you getting these states, or where are you getting these individual states, or where are you getting this energy for comparing these two electrons? Basically, if you look at the Fermi sphere of the normal metal before it became superconducting, you will get a continuous distribution of state with a small broadening, temperature broadening. Okay. So now, if you look at what is the phonon frequency or energy available at that temperature, the phonon frequency is always the Debye frequency, or omega d. That is what is available at that temperature. So the states near the Fermi energy, on either side of the Fermi energy, which are covered by half h bar omega d, in that window will combine and condense onto the Fermi energy EF. Okay, so half h bar omega d on either side of the Fermi distribution, or either side of the Fermi energy, which are covered by the Debye energy or Debye frequency. They will combine, all those electrons will combine and condense onto the level ground state, which is right at the Fermi energy. So the energy gap for this individual particle or single particle excitation, that is how much energy that you need to supply to break this pair. These are the copper pair. is given by 3.5 kb Tc at 0 Kelvin. And this will decrease 0 at Tc, because Tc is where you are going to get this copper pair. When you increase the temperature, this energy gap will reduce, and eventually the gap will close at Tc, the critical temperature. So in nutshell, what we have is, we have two electrons or two fermions which combines, which is mediated by the exchange of phonons, is going to condense onto, it will become a boson and condense onto a single state. And generally this state is called condensate, because all these bosons would like to go and undergo condensation to one single state. So we call it a condensate. The copper pairs are actually condensate, and it lies on one energy level, one state with one wave function. Okay. So there is no separate wave function for separate copper pairs, just one wave function, because it is basically one state throughout, and that state lies at the Fermi energy EF. Okay. Now, just to summarize the other properties of superconductors, as we just discussed, the repulsive electron-electron interaction is modified by the lattice to make it attractive and form copper pairs. And as we know, the superconductivity is a low temperature phenomenon, because the temperature should not break the energy by which the temperature energy or thermal energy should not break these pairs. Okay, so the binding energy of these pairs should be higher than the temperature where it exists. Okay, for temperature, energy should not be sufficient or high that these pairs are broken and become normal electrons. And since the formation of the copper pair involves the lattice also, it's actually kind of a coherent state with the lattice itself, because lattice is the one which mediates the attraction between the two electrons forming the copper pair. So there is no collision with the lattice there. Okay. And secondly, all these charge carriers are actually copper pairs. These charge carriers are copper pairs, are in the same state, one state. And there are no states nearby. So you had a Fermi distribution, and the Fermi energy EF. Okay, you had all electrons at the Fermi energy, but these states now condense onto one single state at Fermi energy, and all the other states for electron single particles are away, or there is an energy gap, which is generally referred to as 2 delta, and there are no states within the gap for copper pairs, because copper pairs would like to condense into one state, and there's only one state there, and there are no states for the electrons to scatter within the gap. What that means is, as long as the applied voltage is not sufficient to break this copper pair, the energy that the copper pairs are gaining is not sufficient to break it into individual electrons. These copper pairs cannot scatter, or there is no resistance to the flow of current. Okay, because there are no states to scatter, the resistance comes from scattering. It's one single state, one single wave function. Okay, you cannot see this, or there are individual Cooper pairs or individual electrons. It is this one single state which extends from one end to the other end of the sample, and that lies at the Fermi energy. So if the applied voltage to run the current through system is small, less than the energy gap, then there will not be any resistance to the flow of current, which is the origin of zero resistance or superconductivity. Now, the coherence length, which is the maximum distance up to which the state of the paired electrons are correlated to produce superconductivity. Okay. So this coherence length generally is given by h bar Vf. Vf is the Fermi velocity divided by 2 delta. Okay. Now, there is another very important aspect of this superconductor, that is Meissner effect, that we will discuss in the next slide. But just before that, the application of magnetic field is going to reduce the transition temperature. So what happens is, when you apply the magnetic field, which is at value BC, which is called critical field, then the superconductor becomes normal. It will be normal material or normal metal. And the relation between the critical field and the TC is of this form. Product of the BC over TC is given here. So when the temperature, the critical temperature TC will have a maximum value when magnetic field is 0, and they have a Vc and Hc as a quadratic dependence. Now, just to review the Meissner effect. Meissner effect is a phenomena where the magnetic field is pushed out of a superconductor. So if you start with a superconducting sample, but it is not in the superconducting state, a superconducting material which is not superconducting, that means the temperature is above Tc, and you apply magnetic field, the magnetic field will pass through the material. But when you reduce the temperature to make it superconducting, suddenly at Tc, all the field lines will be pushed out of this material, and the field inside will be 0. So the total field inside is the applied field plus the magnetization, which is 0. What that means is superconductor is a perfect diamagnetic material. That's what it means. Okay. Now, though the field was pushed out from the material, there is still some penetration of the field into the superconducting material. Okay. And that penetration length is called London penetration length. It is given by this formula here. Okay. This is a distance by which the flux density into the material falls by 1 by eth value of that at the surface. Now, there is an associated phenomena that is called critical current. So critical current is the maximum current that you can pass through a superconductor before it relaxes to the normal state. So if the current is critical current, at critical current, the superconductor turns normal. This is also another form of Meissner effect or field penetration, because what happens is, when you run a current through system, the current will develop a magnetic field, and that magnetic field is proportional to the current, and at the critical current, the magnetic field developed is actually BC, the critical field. At critical field, TC will be 0, or the material becomes normal. So this current turns the material into normal by the field it has generated on the surface of material. Running a current through a superconductor is like applying a magnetic field. When the current is high, the field also will be high, and at IC, at critical current, the field will be the critical field. So typically, this is a cartoon of the critical IV, current voltage characteristics, where there will not be any voltage developed until the critical current is reached. Suddenly there will be a resistance, and there will be a voltage developed, and the resistance will be equal to the normal state resistance of the material. There is no voltage developed in this region because the resistance is 0. Okay, but suddenly when the current reaches critical current, the material will start turning into normal. It will develop some resistance, so there will be a voltage developed across it, and eventually the material becomes normal. Okay. A very important transport parameter is the density of states. Now let's back off and a little bit and look at what happens to density of states in a normal metal or normal conductor right before the transition has happened. Okay. So it's a three-dimensional material, that is what we are considering. So the density of states is going to go like e to the power 1/2, smoothly varying, and the Fermi level is somewhere here. Okay. And electrons in an energy window which is given by 2 delta, this is defined at T equals 0 Kelvin. Okay. All these electrons within this energy window will condense onto one single state, and all the Cooper pairs will be at EF, and there are no other states once the normal conductor turns into superconductor. So there will not be any state available for electrons within this 2 delta window, and all these Cooper pairs are actually bosons. They will condense onto this single state at EF. And also the spatial extension of this pair wave function could be hundreds of micrometer, and coherence length is also somewhat in the same order. And the single particle density of states, when I say single particle density of states, those are the density of states for electrons. As we discussed, when the energy is less than delta, this is referred from the Fermi energy, the single particle density of state is 0. Now, when the energy is more than delta, then the single particle density of state is given by this formula, where E square is the energy and delta is the superconducting gap. Okay. Now, the energy gap as a function of temperature varies by this expression, and this is valid when it is more close to the transition temperature Tc. So it's more or less constant with temperature, but as the Tc is reached, it's going to take this form. So this formula is more applicable when the temperature is close to Tc. So at very low temperature, close to absolute zero, far away from the Tc, the energy gap is 2 delta, and there are no states for electrons or single particles, and this state is for the Cooper pair, and you will have Cooper pairs there. And as you increase the temperature, the gap will reduce by this formula, and you'll also have some states in this side slowly populating because of the temperature. This situation is for absolute zero. And as you reduce the temperature, increase the temperature further, you'll close the gap, you'll have more and more states populated here at the expense of some states here. And eventually, when the temperature crosses over Tc, you will have a normal density of state distribution for a three-dimensional material. So this is how the density of state is going to vary, or the states or the occupation going to vary in a superconductor as a function of temperature. Whenever I say occupation, it refers to quasi-particles, it refers to single particle or electrons, not for Cooper pairs. Cooper pairs always reside, or it's always condensed into a state right at the Fermi energy. Okay. Now, every transport mechanism involves injecting and taking charges out of the superconductor, and it invariably involves other materials such as metals, semiconductors, or another superconductor. To put or remove charge from a superconductor, or to run a current through a superconductor, or to apply voltage onto a superconductor, you always need something like a normal metal. That is what you use to connect from your voltage source or the amplifier to the superconductor. Okay. Now, let us look at the density of state for a normal metal and a superconductor, and consider the transport mechanism when the applied voltage is less than the superconducting gap delta. Okay, so that is the situation. You have normal metal on one side and you have superconductor on the other side, and as you know, the occupation or the states are completely filled on the normal metal side until Fermi energy. And also on the superconductor side, you have a gap of 2 delta, right at the Fermi energy for electrons. And all the states until this are filled, and these states are empty. But there is a state right at the Fermi energy for the superconductor, but that is only for Cooper pairs. Those are not for electrons. So now, when you apply voltage which is less than the superconducting gap delta is the energy spacing between the Cooper pair level and the next available or higher quasi-particle level or electron level. Okay, so this electron from here cannot go here because this state is only for Cooper pair. This is not for electron. If the electron goes here, of course there are no states that will combine and become Cooper pair. Okay, so electron cannot go here. Now, electron cannot go here either because this state is high up in the energy and it is not accessible by the voltage that you have applied. So naturally, for this electron, this interface, the normal metal superconducting interface is actually a barrier. Now, when you apply voltage and push the electron to the interface, what happens is this electron can reflect back. That is a natural process, that's a normal process. So there is a normal reflection of electrons, which doesn't contribute to any net current or charge transfer from the normal metal to the superconductor side. So no net current will flow because of this reflection. But then there is another interesting process which is called anti-reflection, which is the only way you can run a current from a normal metal to superconductor when the voltage is small, when the voltage is less than delta. This process is called anti-reflection. It happens when the applied voltage VSD or the energy due to the applied voltage is less than the superconducting gap. The mechanism is illustrated here. What happens is, say an electron is approaching the junction, approaching the interface from the metal side, normal metal side, then naturally it cannot go here. But if another electron is available right at the interface, then this electron can combine with this electron and form a Cooper pair, provided the momentum and the spin states are actually matching, which is not a huge issue because you have huge number of electrons on the metal side, and you always will find another electron with opposite momentum and opposite spin. That is not that's not that hard, and that's very easy. And always there are electrons available, matching electrons available. So, but then what happens is we need to have the charge conserved and the energy conserved, right? So this electron will come from at an energy exactly the same amount below the Fermi energy. Okay, you have an electron here, so you have an electron coming exactly the same energy from here. Then what happens is a hole will be developed. That hole will backtrack or will move in the opposite direction. Hole will reflect back. Electron will go, this is the electron you have injected into the interface, then we'll pick up another electron, then that hole which is left behind will travel in the reverse direction. So these two are actually complementary. So their charge will cancel each other. So you are actually injecting only one electron from this side, from the source. But you'll pick up another electron from here, then the hole which will travel back. Okay. Now, these two electrons will form a Cooper pair, and that will travel to the next interface, other interface. Okay, that is the process. Now, the net charge that is transferred from the left side, that is the normal metal side, to the Cooper pair side or the superconductor is 2E. Okay. So this is the only process you can have when the applied voltage is less than the energy gap. This is only the process of transport. But when the voltage is, or energy to the voltage is above the superconducting gap, this process is always allowed. You can have electron directly going here, that we will discuss in the next lecture of this module, where the application of voltage will tilt or shift the position of the states on the superconductor side with respect to metal side, and you can have the empty states for quasi-particle, these aligns with the Fermi energy here when you apply sufficient voltage across the junction. Okay, but anti-reflection is a process when the voltage is low. Okay, now this anti-reflection you can analyze using the transmission formalism or transmission problem. So what we have is, you have electron going to the interface from the metal side, and you have hole leaving the interface from the superconducting side. Okay, and you have two electrons traveling into superconductor. So you can visualize this as a kind of three-terminal problem where you have electron lead, and there is a hole lead, then there is a Cooper pair lead. Okay, so electron going to the superconductor and the hole leaving the superconductor, and the superconductor is something like which converts the incoming electrons in the electron lead into outgoing electrons on the hole lead. So superconductor takes the electron from the metal side, converts that and push the hole back into the metal. In the process, this will take two electrons into it. So the probability for the electron to hole conversion is the probability for anti-reflection, or EH, where EH stands for electron to hole, and REH is amplitude of anti-reflection, and square of that is the probability for the reflection to happen. And we know from the conductance formalism, the conductance across the interface is G0, that is the quantum limit of conduction, G0 into the probability for reflection. Because if the anti-reflection happens, then 2E goes into superconductor. Though we call it a reflection, it's actually a transmission probability, because anti-reflection is a reflection of the hole, but it actually transmits one more electron into the superconductor side. So if the probability for anti-reflection is 1, then 2 electrons are gone into superconductor, and this 2 factor stands for the 2 there. Though you are pushing 1 electron from the metal side, 2 electrons are actually going to the superconductor. So this 2 stands for that factor. G0 stands for the quantum limit of conduction, and REH square stands for the probability of that process to happen. Okay. So now, just to summarize, anti-reflection is the process by which you can get current flowing from normal metal to superconductor and from superconductor to normal metal on the other end when the applied voltage is less than the superconducting gap. And anti-reflection you can treat as a transmission problem where the transmission probability is the probability for the anti-reflection, and you will get the conductance as 2G0 into REH square, where REH is the amplitude for the anti-reflection, or square is the probability for anti-reflection, and G0 is the conductance quantum. Okay. Now, let's quickly review a simple technique to fabricate mesoscopic superconducting junction system. What we just discussed is a junction between superconductor and normal metal. Similarly, you can have superconductor-superconductor junctions between same superconductor, or also you can have superconductor-superconductor junction between different superconductor. You can also have superconductor insulator superconducting junction. It's a tunnel junction between two superconductor too. Okay, so all these junctions and their transport mechanism we will discuss in the next lecture, but let's quickly review okay, the fabrication process by which you can make these junctions in the lab. So the fabrication process is similar to making other micro scale or nanoscale devices, which we have reviewed in one of the initial lectures. So what we have is you have a geometry which is defined by electron beam lithography. The lithography process involves coating the substrate with the electron beam sensitive polymers. We call it electron beam resist. Once the resist is exposed to the electron beam, it will undergo chemical change and you can develop and you can get a pattern, which whatever pattern you have drawn. Then after that, what you would do is, after developing, you will evaporate superconducting material into it at two different angles, which is going to cast shadow of one on the other, and there is an oxidation step in the middle. So just to expand this further, imagine that this is the pattern that you have got after the lithography. Okay, the pattern looks like this. Now what you would do is you will metallize by a process called thermal evaporation or electron beam evaporation. It's called physical vapor deposition. Okay, from one angle. Once you do that, you will get something like the yellow region here. So you will get a region which looks something like this. Okay, this yellow here, this one, and this yellow region here, only that. Okay, now what you will do next is you would admit some oxygen or mixture of oxygen and some other inert gas into this chamber, which will quickly oxidize the material that you have deposited. The first material normally is always or almost always aluminum, which is a superconductor, and when you admit oxygen inside the chamber, you will form a thin layer of aluminum oxide. And after that, what you would do is, you would, after the formation of the oxide, you will pump out the oxygen, whatever we have put inside the chamber. Then you will do a second evaporation, but that will be from a different angle. So what you will get is, you will get one evaporation, you will get this yellow shaped region. Then you have oxide on top of it, and the next evaporation you will get, because that is done at a different angle, you will get a displaced pattern which looks more like the green thing here. Okay, this you don't need to worry about. This is a floating piece of metal which is not going to be a part of the circuit. This is not going to be a part of circuit. But what you got is, you got a superconductor then which is oxidized. So there is a thin insulating layer in the middle. Then you get another superconductor that is a result of the second evaporation. So what you have is, you have first evaporation gave you this, then there is an oxide layer, the second evaporation gave you this, then you have superconductor, oxide, then superconductor. So there is a junction. This is an actual pattern where you can see two shadows there. That is why it's called a shadow evaporation, because you evaporate in one angle, oxidize, then you evaporate from the other angle, but there is an oxidation step in the middle. So here you have the junction between this and this, but this is a result of one evaporation, and this is the result of the second evaporation. Okay, this happened during one evaporation. Okay, this happened during the other evaporation, and here these two ends, they overlap with a thin layer of oxide in the middle, so that is a tunnel junction. So what we got here is a superconductor, insulator, superconductor, insulator, superconductor junction. So you have superconductor, then there is an insulator, then superconductor, that is this part, then there is an insulator, that is this junction, then again you have superconductor, that is this part. Okay, so you got basically two SIS, superconductor insulator superconductor junction by this process. Okay, same story here also. You have superconductor here, superconductor here, superconductor here, and you have two junctions in this case. This is called shadow evaporation because you are doing the same pattern but two different angles is going to cast a shadow of the same pattern. Okay, that is why it's called shadow evaporation. By cleverly designing your pattern and drawing it, you can make many junctions. Here this is an array of junctions, so you have junction every point here. Okay, this is an array of superconductor, insulator, superconductor junction. This is a one-dimensional array. Say 1D array of superconductor, 1D array, superconductor, insulator, superconductor junction. This is a 2D array. You can have two-dimensional array of SIS junctions. That's what it is. Okay. Again, the only thing is you need to cleverly design the pattern and cleverly choose the angle of tilting when you metallize it. So here we have junctions at every point. So you have, it's a two-dimensional array of junctions. All you need is just need to tilt two angles between, and you need an oxidation step in the middle. Okay, so by this let's stop here, and we will continue the discussion of this tunneling process across these junctions that we just made in the next lecture. Okay.